Hi class, we are on to chapter 9.4. We're going to talk about vectors in three dimensions. So just like the last section was an extension of two dimensions where we start talking about three-dimensional geometry, everything was pretty much the same as two-dimensional geometry except we had to consider a third variable. Here it's the same thing. Everything that we do with vectors in two dimensions we can do in three dimensions. We just have to consider the third term. In what's called linear algebra, the study of vectors, we actually consider vectors to be n-dimensional. So it can be 10 terms, it could be 12, 100, it can be an infinite number of terms. So all the things that we do in two dimensions, we can pretty much extend to happen in any number of dimensions that we want, okay? But for the purposes of calculus, we tend to stick to three dimensions because we live in a three-dimensional world. So this being a pre-cal class, we're going to talk about vectors in three dimensions today. So again, in the same way that we were able to extend R2 to R3 by just considering an extra variable, we're going to do the same thing with vectors, right? So all of our rules for vectors in 3 space are the same as the rules we had in 2 space. We're just using that extra coordinate, right? So the component form of a vector in 3 space is the same as the component form in 2 space, except for now we have an extra variable. So if I have an initial point of P naught, which is X naught, Y naught, Z naught, and a terminal point of P1, X1, Y1, Z1, then our vector V, right, that has initial point P naught and terminal point P1, we can describe it as the differences between each of those components, right? So our vector V is X1 minus X naught, Y1 minus Y naught, and Z1 minus Z naught. So it's literally the same exact thing. We just now are including this third term, right? We want to find the magnitude of a vector. The formulas is exactly the same. We are taking each term of V, we are squaring it, we're adding it together, and we're taking the square root, because we saw before that length in 3 dimensions is really just, again, an extension of the distance formula in 2 dimensions. And remember, magnitude, or the length of a vector, is just the distance formula, right? So magnitude of a vector is v1 squared, second term squared, third term squared. Add those together, take its square root, okay? So again, now that we have a new axis, we can represent any vector in terms of standard unit vectors, just like we could before. However, before our standard unit vectors was I and j. Now we have k. So before we only had 2 axes, now we have 3, so we need a third standard unit vector. So I is, instead of 1, 0, we have to include that third dimension. J is 0, 1, 0, and k will be 0, 0, 1. Right, so this points in the x direction, points in the y direction, points in the z direction. So let's look at an example. I can represent my vector A equals negative 2, 3, 1 as negative 2 times I, right, in the x direction, plus 3 in the j direction, plus 1 in the k direction. So negative 2i plus 3j plus k is another way to represent this vector. Okay, so dot product. Formula for dot product doesn't change at all. Okay, if I want to find the dot product between V and U, I still multiply each element times its respective element in the other vector, add all of those products together, and that's my dot product, right? So V times U is the 2 first elements multiplied plus the 2 second elements multiplied plus the 2 third elements multiplied. If theta is the angle between my vectors, then I can use the geometric representation. I find the length of V, I find the length of U, and the cosine of the angle between them. If I know it, if I don't know the angle between them, then I just take this equation and solve for theta, and it's the exact same equation. Theta is cosine inverse dot product over the product of the lengths. So what's new for us now is the direction angles of a vector. Okay, so say that we have a non-zero vector, okay, whose components are v1, v2, v3, so they're not all 0. Then we have 3 angles that are formed. right, our vector forms not just an angle with the x and y axis like it did before, but now it forms an angle with the x-axis, the y-axis, and the z-axis. Okay, one with each axis. So before we had theta with the x-axis and pi minus 2 minus my angle with the y-axis. So again, let's say I had a vector that formed a 30-degree angle with the x-axis, then the remaining angle with the y-axis was 60 degrees, right? So pi over 2 minus theta. So we still have that, but now that we have a new axis involved, we'll have our three angles, which we'll call alpha, beta, and gamma. Okay, alpha, beta, gamma. So alpha makes an angle with x, beta makes an angle with y, and gamma is our angle formed with our vector and the z-axis. Okay, so I have some vector v2, so I had to come out some amount v1, then over some amount v2, and then up some amount v3. So with the x-axis, we can think about the angle formed as, like, let's say I projected this down onto the xy plane. I'd have some angle onto that shadow cast. I'd have some other angle between y and that shadow cast. And for v3, I can just think about it the same way, but I'm projecting it onto, well, let's say the YZ axis, right? So the closest direction between the axis z and this vector is the angle formed. The closest angle between x and this vector is the angle formed, and the closest, the most direct line or plane between y and this vector is the angle that I'm considering. So here I have A, or alpha. Here this is beta, and then up top is my gamma angle. Okay, remember that V1 is equal to the magnitude of V times cosine of alpha. Remember, we always think about this as a circle with the radius of the length of the vector. So V1 is me moving this direction along V1, right? And that cosine of alpha that's formed with this angle, right? That's how I get to V1. I'm directly along the x-axis. If I want to solve for cosine of alpha, well, that's V1 over the length of V. Okay, so we can extend this to look at the other two angles also, right? So cosine of alpha is V1 over length of V. Cosine of beta, right? So this angle is V2 over length of V, and cosine gamma is V3 over the length of V, right? One of the properties of this direction of my cosines is that if I square each one of these cosine lengths, cosine alpha, cosine squared beta plus cosine squared gamma, I will get out a value of 1.